When he applied this theory for moving electron, he is able to calculate the lambda, that is wavelength of electron, as 4 into 10 to the power of minus 5 centimeters in hydrogen. When the revolving electron wavelength is calculated by using lambda is equal to h by mv formula, he is able to calculate that value. Already we know electron is a subatomic particle. It has the mass, is it not? So from this, when it is associated with lambda and it is possessing the mass, from these two we can establish GL nature of electron. That is, it can behave both as particle as well as wave. Now, the particle nature and wave nature, where we can observe these two. Particle nature, just you remember, mostly stationary electrons. Stationary means almost all slow moving, almost all they are standing electrons. Electrons behave like particles. Remember, stationary electrons behave like particles. And whereas moving electrons, this is moving electrons behave like waves, like wave. And now what are the characteristic features that support? Simply particle nature. This particle nature is observed. Particle nature, it is observed when from scintillations. Scintillations, that is nothing but when the electrons are falling on the photographic plate, some sort of scintillations, brightening sparks will appear. And one more, it is nothing but the scintillation itself indicates the particle natures of the electron. And wave nature, where we can observe this wave nature of the electron. It is simply when it is revolving around the nucleus, it behaves like a 3D wave. It behaves like a 3D wave. When around the nucleus it is revolving, it behaves like a 3D wave and it possesses the wavelength. Scintillation indicates the particle nature of the electron. And these are the two characteristic features that support the particle as well as the wave nature of the electrons. Clear? And not only scintillation, photoelectric effect also. Photoelectric effect. When electrons are coming out, it is also the support for the particle nature. While electron is moving, it behaves like a wave because it is associated with the wavelength. Clear? And now, this one, when it is of de Broglie's wave equation, de Broglie's wave equation. How far it is useful for our calculations in competitive exams? Actually, lambda is equal to h by mv, and we know m, mass of the particle, into velocity of the particle gives p. P is nothing but momentum. So simply we can write this lambda is equal to h by p. And with all these, let us derive the other forms. In this case, if lambda 1 is equal to h by m1 v1, lambda 2 is equal to h by m2 v2. Now, if we are considering the ratio lambda 1 by lambda 2, it appears as m2 v2 by m1 v1. This is one form. And the other one is here different conditions. If M1 is equal to M2, that means masses of the particles are same. Then how we can convert this? Yes, lambda 1 by lambda 2 is equal to M2 by M1. This is when, sorry, not M2 by M1. Already M1 is equal to M2, and hence here we can say V2 by V1. This is one form. And the second case is if V1 is equal to V2, that is both the two particles are moving with the same velocity, then the wavelength associated with them will be related as inversely related to their masses. This is another form. And now from this equation also, if directly they are providing this one, lambda 1 is equal to h by momentum of that particle 1, and lambda 2 is equal to h by momentum of particle 2. Now lambda 1 by lambda 2 is p2 by p1. Any of these relations, simply they are, sometimes they are giving numerical, and some other cases they are providing just the relations. Are you clear with this one? Now the other forms, other derived forms of these lambda is equal to h by mv, from this one other derived forms are there. Let us derive that one. Derived forms of de Broglie wave equation. In this one, first one, if lambda is equal to h by mv, okay, and this is lambda is equal to h by mv. But this mv we can obtain from kinetic energy instead of mass and volume, velocity. If for any particle kinetic energy is given, then the kinetic energy is also related to this wavelength. How? Kinetic energy and lambda. First one. As we know, kinetic energy Ke is equal to half mv square. Kinetic energy Ke is half mv square. And if we are considering this as mv square, then we can write this as 2Ke. Is it not? And now, when on both sides multiplied with both sides multiplied with m, it is required the mass of the particle. Then what we are getting here, already m is there. M into m square v square is equal to 2Ke into m. But what we require? mv. So from this relation, mv is equal to under root of 2 into kinetic energy into m. So instead of mv, now we can write this kinetic, that is under root 2 Kem. Hence, here we are getting lambda is equal to h by under root 2 Ke into m. This is the relation between wavelength and kinetic energy, one derived form. And one more is nothing but it is considered as Davison and Gerner. Actually, this Davison and Gerner's experiments, these experiments are supporting for the particle nature of the, not particle nature, wave nature of the electron. Davison and Gerner's experiments are supporting for the wave nature of the electron also. Clear? And now this Davison and Gerner, they are considering that if a charged particle like electron, let us count E. E is the charge, like electron, E charge. It is negative charge. Representation is E, and it is also taken as the charge now. Is accelerated by a potential V. V potential is used on E charge. Now the charged particle will get kinetic energy. Do you know the relation between these? Yes, that kinetic energy, which is nothing but half mv square, now becomes equal to charge and potential. So now from this relation we have to consider mv, and here when it is half mv square is ev, mv square is equal to 2ev. E is charge of the particle and v is nothing but the velocity. Now on both sides multiplied with m, similar to this one, then what we are getting is m square v square is equal to 2 e v m. But what we require? mv. Hence mv from this relation is equal to under root 2 e v m. This is mv. And now de Broglie's wave equation, lambda is equal to h by mv. Instead of the mv, we can write h by under root 2 e v m. Here E is the charge. If here let me write, if particle has a charge Q, then the same equation, this equation we can write as lambda is equal to h by under root 2, instead of E we can write Q, V potential, mass of the particle. This is Davison-Gerner's modification for de Broglie's wave equation. Are you clear? This is nothing but from the same concept, lambda is equal to h by mv. We are getting that mv values from different data. It may be from kinetic energy, or it may be from for charged particles only. For charged particles, it may be from the charge and the potential, which is useful in accelerating the particle. This modification has been given by Davison and Gerner. Are you clear? Now, after deriving this, for charged particles, very familiar, that is nothing but charged particles in atomic structure, electron, yes, proton, and alpha particle. Initially, in the beginning of this atomic structure, what we studied, the specific charges for proton, electron, and then it is for alpha particle, because 2 units of charge, 4 units of mass. So like that for charged particles, for neutral particles like neutron and molecule, how this de Broglie's wave equation is obtained. For the direct formulation, here I am giving the relation for competitive exams or competitions. And you have to remember, after derivation, when you are substituting all the values, finally you are getting this. First one is for in case of charged particles. The first one is nothing but electron. For electron, wavelength is equal to 12.27 by under root V. V is nothing but the potential applied for accelerating that particle. Angstrom unit. So when they are asking for wavelength of the electron, simply you can write by providing the potential. Then you can write this formula. And in case of proton, the second one is proton. Proton is nothing but H plus. And for this H plus, lambda H plus or proton is equal to 0.286 by under root V. Again potential angstrom units. And now for alpha particle, which is considered to be helium nucleus, He plus 2, 4. Here for alpha particle, lambda is equal to 0.101 by under root V angstrom units. These are the values. Directly you can substitute because it is competitive exam time bound. So immediately when they are providing the potential which is of useful in accelerating the particle like electron or proton or alpha particle, you can substitute the values. Now coming to neutral particles. Second application is for neutral particles. In case of neutral particles, and when we are considering neutral particle, the first one, subatomic particle, what we are having in our idea is nothing but neutron. It is not possible to accelerate this, is it not? But some energy will be provided to that to move. In such a case, for neutron, lambda n is equal to 0.286 by, instead of V, it is given energy provided to that in electron volts. And for molecules, just it is for neutral gas molecules. Molecules are also not having any charge. In such a case, this lambda is given as h by, not the fixed value, it is Planck's constant, h by m v. V is RMS velocity. Now, in our chemistry, this gaseous state is removed. It is deleted. But in physics, you can learn that what is RMS velocity. Most probable velocity, RMS velocity, average velocity, like 3 types of molecular velocities for gases. So, of them, only RMS velocity is taken. Here it is RMS velocity. Let me write V RMS. M V RMS velocity. And this can be written like this. Lambda is equal to h by m under root 3 kt. Here k is nothing but Boltzmann constant. I think you know this Boltzmann constant. It is again from gaseous state. That is nothing but R by N naught is Boltzmann constant. R is nothing but gas constant, N naught is Avogadro number. So, in this manner, you can directly calculate the wavelengths of different particles, like charged particles as well as for neutral particles. Are you clear? Be thorough with this one because it is time bound exam. For competitive exams, they are giving question and directly asking the optional, that is nothing but objective mode. You have to solve and you have to select the correct option. Is it not? So, this is about the de Broglie's wave equation. Now, one more discussion. How this de Broglie wave equation is supporting Bohr's concept. Let me explain. It is Bohr's concept and de Broglie's wave equation. And for this purpose, first of all, we should know what is the Bohr's quantum condition. Main concept. You know, when nucleus is having the positive charge and the neutrons inside, electrons are revolving around the nucleus in circular paths known as orbits. In which orbit the electron is revolving? There the condition is given. Yes. In which orbit the angular momentum of electron, that is mvr, is equal to multiple of h by 2 pi. Here n is nothing but the orbit number. That is simply Bohr's quantum condition we are giving as mvr is equal to nh by 2 pi. This is Bohr's concept. Are you clear? Now, how de Broglie's wave equation supports this? Simply, first of all, what is de Broglie wave equation? De Broglie's, just now we derived it. De Broglie's wave equation is lambda is equal to h by mv. Is it not? And one more, his concept regarding the electrons is whenever the electron is revolving around the nucleus in an orbit, it behaves like a stationary wave, three-dimensional wave in a phase, out of phase. Two conditions are there. In a phase means the starting and the ending of this wave we don't know. Out of phase, just let me draw one diagram to explain the out of phase. In case if electron is out of phase, simply its movement will like this. The ends are not met. They are not met to each other. Simply they end in their positions. But here it is not that such type of condition. There is no beginning, no ending. It is continuously revolving around the nucleus. As a three-dimensional, it will cover x, y, z directions around the nucleus. And here he is considering one more very interesting factor. That is, when it is of revolving around these, here different wavelengths between two crests or troughs, the distance is wavelength. In an orbit, when the three-dimensional wave behaving electron is revolving, the wavelength numbers, that is number of wavelengths associated, is equal to the circumference of that orbit, that is n lambda is equal to 2 pi r. 2 pi r is nothing but circumference of the orbit and n is nothing but that orbit number. If in first orbit only one wavelength will be there, and that one wavelength is equal to the first orbit circumference. If it is second orbit, two wavelengths equal to circumference of second orbit. Third, three wavelengths, four, like that. This is the condition what he proposed. And now from this, when n lambda is equal to 2 pi r, simply we can write lambda is equal to 2 pi r by n. But already lambda is h by mv proved. So simply that value we can substitute in this equation where we are getting h by mv is equal to 2 pi r by n. And this on rearranging, just try to rearrange. Let me draw this. It is nothing but mv and r on one side. the remaining on the other side. So now let me write that these M, V, R. When all these three are on one side, this will go to this N, H, by. This will come to new denominator 2 pi. That is nothing but MVR is equal to NH by 2 pi, which is nothing but Bohr's quantum condition. From de Broglie's wave equation, by proposing this three-dimensional wave behavior of the electron, which is revolving around the nucleus, by combining these two relations, he is of now supporting the Bohr's quantum condition. That's why we can say that de Broglie's proposals are in according or in agreement with the Bohr's concept. Are you clear? That is about the first modern approach for atomic model. In the next class, what are the objections raised by Heisenberg and how many derived forms for that Heisenberg's uncertainty principle? All these we will discuss in the next class. Okay, thank you.